RL78 uses an optimized 16-bit CPU with Harvard architecture with a full 16-bit data bus for RAM, CPU registers and peripherals, and a 3-stage pipeline. Even though the RL78 uses a CISC instruction set, 86% of the instructions are executed in 1 to 2 clock cycles at the full 32 MHz clock speed. This high performance yields a Drystone 2.1 benchmark of 1.39 Drystone MIPS per megahertz, or about 44.5 Drystone MIPS total at 32 MHz operation. Additionally, instruction lengths are in increments of bytes, sizes of 1 to 6 bytes instead of full multiples of 16-bit words, so the fine granularity of instruction length reduces the overall code size. Also, the RL78 MCU has hardware facilities to assist with math functions such as multiply, accumulate, and divide. The multiply and mac are executed in 1 and 2 cycles, respectively. The RL78 barrel shift function, typically found on DSPs and 32-bit MCUs, can execute a 32-bit data shift or rotate with 1 to 15-bit positions in just 1 clock cycle. Up to 4 independent DMA channels allow any peripheral data transfer, 2 from RAM memory in 2 clock cycles. However, some RL78 MCUs have DTC or data transfer control with more flexibility and more channels available for peripheral data function. Getting into the application side, what is near sensor processing? There are 2 main ways to monitor the environment and report data back to a monitoring center. One method is to record all events and try to provide live telemetry, with all raw data sent back to the central monitoring point. We can easily see the difficulty of this strategy. Data latencies causing loss of real-time reporting, needing large communication bandwidth, consuming lots of communication connection power, plus putting a huge load on the data concentration center, etc. An alternate method is to take average samples and only report back key environmental changes to the monitoring center. Some events are more critical than others. For example, do we need to report temperature once per second? So if we can sample data, process and average the data, reject outlying data points due to noise or interference, and then send a concentrated but succinct data set, we're better off. What is swap? Swap is size, weight, and power. Reducing size, weight, and power leads to lower costs and simpler system complexity in a near sensor design. Near sensor processing designs are seeing increasing requirements to capture more data and more complex types of analog phenomena to process that data quickly and deliver it more swiftly than ever before. RL78 MCUs enable near sensor processing and reduce swap. In this RL78 near sensor processing example, fire detection sensor nodes can be kept in standby, sampling smoke or heat every few minutes. A small solar panel can keep a small lithium-ion battery charged since average sensor node current drain is low. The system is mostly in standby, drawing microamps or less, and experiences peak current drain when sampling an event or communicating over the wireless network. In this case, the RL78 MCU processes the data, like heat, moisture, or smoke, and manages the wake-up timing for each sensor, while also managing the wireless RF module. Key features of RL78 to reduce swap for near sensor processing are highly integrated analog peripherals such as ADCs, DACs, programmable gain amplifiers, comparators, op-amps, and analog muxes. The ability and agility of RL78 MCU architecture to quickly shift from stop standby mode at less than 1 microamp current drain to full speed 32 MHz operation. Then, low standby and CPU run currents, special power saving modes like halt, stop, and snooze mode, efficient 16-bit instruction processing with 86% of instructions completing in 1 to 2 CPU cycles, a single cycle 16-bit barrel shifter for shift and rotates, and finally a 1 cycle 16 by 16 multiply and 2 cycle 16-bit MAC instruction.